Welcome to a brief introduction to the effect of chlorofluorocarbons on the ozone layer. This is a topic that's commonly taught in general chemistry courses, and I thought it would be fun to take a look at it and see if we could animate the mechanism by which the chlorofluorocarbons that get into the upper atmosphere do so much damage. But before we do that, let's take a look at what it's protecting us from. Now, the sun emits a lot of different wavelengths of light, but one of those is what we call the UVC radiation. And UVC radiation is very high energy ultraviolet light, which would be very damaging if it were to reach the Earth's surface and come into contact with us. It would damage our DNA, give us sunburns, and make things generally pretty unpleasant on the surface of the Earth. But we're protected by a layer of ozone which accumulates in the upper atmosphere of the Earth and absorbs that UVC radiation before it can get to us. And chlorofluorocarbons throw a monkey wrench into that whole system. So let's take a look at how. Again, we have UVC radiation bombarding the planet constantly. But as long as there's ozone there, we're safe. Of course, if the ozone were to somehow become depleted and a hole were to form, then we would have a lot of high-energy UVC light reaching the Earth's surface. And again, that would be bad news for humanity. Now, what you need to understand about the ozone layer is that it's not just ozone. In the upper atmosphere, some pretty funky forms of oxygen can exist, not just the O3 ozone molecule, but also atomic oxygen and the usual diatomic oxygen that we're used to seeing at the surface of the Earth. And all of these species are in equilibrium with one another, meaning they interconvert between being an O3 and an O and being two O2s. So what's really going on here is this constant interconversion back and forth. But it always leaves a little bit of ozone there. You notice that in this equilibrium there's always some O3. And that's good news for us because we need that O3 there. Now, the problem that comes with the use of chlorofluorocarbons is that as they reach the upper atmosphere, they change that equilibrium in a way that doesn't suit us very well. So, the normal healthy equilibrium involves atomic oxygen and ozone in equilibrium with diatomic oxygen in a reaction with this kind of stoichiometry. O plus O3 goes to 2O2 and back again. But what happens in the upper atmosphere? When we allow something like, in this case, Freon 12 here to reach this ozone hole, which I've shown here in this NASA photograph, showing it over the South Pole. Well, what happens when chlorofluorocarbons get up there is they act as a source of chlorine atoms. And that's what gets the reaction messed up. It's the presence of that chlorine atom which catalyzes the breakdown of ozone into O2. So this equilibrium gets thrown out of balance because the chlorine atoms accelerate the decomposition relative to the reformation of ozone. And that's going to mean that the ozone concentration, where there are chlorine atoms, is going to go down. So let's take a look at exactly how this happens from a chemical reaction standpoint. So here's my Freon 12 molecule on its way into the upper atmosphere, where there's a lot of high energy light reaching that area. And in comes a photon of sufficient energy to break that carbon-chlorine bond, creating the chlorine atom, which causes so much damage. Now, a lone chlorine atom has 7 valence electrons, so it's not very happy. It wants to bond to something. And if you work out your Lewis dot formula for ozone, you'll notice that ozone is not a terribly happy molecule either. And so atomic chlorine and ozone can react to form chlorine monoxide and diatomic oxygen. Now, that would be bad enough if one chlorine atom could decompose one molecule of ozone. But what happens next is what's really disappointing. That atomic oxygen that's up there as well can then react with the chlorine monoxide, forming another molecule of O2, but more importantly, regenerating the chlorine atom, which can then go along its way and react yet again. So you'll notice that in my two-step reaction that I've drawn here on the bottom left, that chlorine goes in as a reactant, but also comes out as a product. And this is our definition of a catalyst. So the chlorine catalyzes the decomposition of ozone into O2. And one chlorine atom can do this to tens or hundreds of thousands of molecules of ozone. And that is the real danger with using CFCs, that just a small amount can provide the catalyst needed to decimate the ozone layer. That's the bad news, folks. The good news is that ozone production, remember, is in equilibrium. So as we finally start to purge some of those chlorine atoms out of the upper atmosphere, the ozone layer should naturally reestablish itself in the appropriate equilibrium. So there's hope for us yet. That's all for now, everybody. I'm Professor Davis from ChemSurvival.com and the YouTube channel ChemSurvival. See you on the next video.